Good afternoon, everyone. My name is Jordan. Today, my teammates, Tim and James and I will be presenting on Guardrail, which is a tool we've been building together over the last 2 months. In brief, Guardrail is an open source tool that generates regression tests for microservices using captured HTTP traffic. Don't worry if this description doesn't quite make sense yet. We'll spend the rest of the presentation breaking down these concepts. We'll first talk about some of the different ways microservices can be tested and the challenges developers encounter as they create those tests. Then we'll talk about traffic replay, which is an approach to testing microservices that addresses those challenges. Finally, we'll talk about how we made Guardrail, which is an implementation of traffic replay. All right, so first let's talk about why developers want to test microservices. We'll base our conversation around this hypothetical scenario. We have a developer named Aaron, who is responsible for maintaining an online store with the service-oriented architecture diagrammed here. As you can see in this architecture, requests from users first hit an API gateway, which then issues requests to the store service, and then the store service issues requests to the shipping service. As the maintainer of the app, Aaron decides to update the store service in order to improve its performance or perhaps integrate a new form of technology. They run their unit tests on the changes they've made to the code and then deploy those changes into the production environment. If the updated microservice handles production traffic as expected, then the update was a success and the store continues to operate without interruption. However, there's also the possibility the updated code, once it's integrated with the other pieces of the microservice, introduced unforeseen changes into the microservice as a whole, and the service starts to mishandle traffic in the production environment. In fact, according to DevOps Research and Assessment's State of DevOps study, 15% of deployed changes cause an incident in production. And we obviously want to avoid these production incidents because they degrade application performance, cause revenue loss for the business, and lead to system-wide outages. Here's what a system-wide outage might look like for Aaron's e-commerce site. If the application has a low fault tolerance, mishandled requests could lead to other services failing and the entire system crashing. From this scenario, we know that Aaron needs to confirm that the new version of the microservice as a whole operates as it is expected to. Another way to say this is we need to test the microservice. And now Aaron needs to decide how to go about doing that test. And there are two broad categories for testing microservices. Those that are done in production, which means the new code is deployed and tested using real traffic, and those done before the service is deployed in production, often using manually scripted traffic. Let's start with what it means to test in production. The principle of testing in production can be applied in many different ways, but one of the most common ways it's applied is through a Canary deployment. So taking our example of Aaron's e-commerce application, if Aaron were to release the new version of the store service using a Canary deployment, they would deploy it to production like our previous example, except this time they would also keep the older version of the service up and running. And then the API gateway would then split requests meant for the store service between the old and new versions, only sending a small portion of that traffic to the new version. By Canary deploying the new version, Aaron is able to confirm whether or not the service as a whole behaves as it is expected to. If after Canary deploying it, the error monitoring system does not notice new errors, Aaron can replace the old version of the store service with the new version. If their error monitoring system does notice new errors, then Aaron simply needs to change the API gateway so that production traffic is no longer being sent to the misbehaving new version, and the production system will have returned to its original functioning state. While testing in production is a good way to test the behavior of an updated microservice, there are cases where it introduces more risks than benefit. For example, in highly regulated software industries like financial or medical applications, a Canary deployment mishandling a few requests could put a company in non-compliance. Or even an example of Aaron's e-commerce store, even if Aaron rolls back the Canary deployment soon after it starts to mishandle requests, those few mishandled requests could lead to a few customers being overcharged, and the business might not be willing to risk that happening. So going forward, let's say that is the case, and testing in production is not a good fit for Aaron. This means we need to find a way to test the microservice without interacting with the production environment. And in order to figure out what that test would look like, let's think about what Aaron is trying to do. Aaron is wanting to replace an old version of a microservice with a newer version of that same microservice. And if you think about that, this means we want to prove that any given request, whether it's issued to the original version of the microservice or the new version, result in the same response. If that's the case, we can say the new version of the microservice is production ready. And this is called a regression test. We're not testing a new additional function of the microservice. We're assuming that the old and new versions of the service will be handling the exact same traffic. And if one is swapped out for the other, the system as a whole won't notice the change. Regression tests don't provide full confidence that a new version of a microservice won't introduce incidents into production. There are bugs and performance issues that a regression test won't catch. For example, we haven't confirmed the service can handle spikes in production traffic. This isn't a load test. But for Aaron's use case, this is a good fit. So regression tests are a good way to confirm that changes being made to the store service are safe to deploy without having to interact with the production environment, as one would with a Canary deployment. Now that we've established that we need to test the behavior of the store service 2.0 as a whole, we need to run those tests outside of production. And we've identified regression tests as a way to do that. We can talk about the challenges developers encounter when they implement those regression tests. Those challenges are generating the requests to issue against the service under test and accessing downstream dependency services. We'll go further into detail about what those challenges mean. First, generating requests to be issued against the updated service. That is, what will these requests be and what will the responses be? One common approach to this challenge is for the developer to manually script the requests based off of their understanding of the application's internal network traffic and the microservices behavior. This is a brief example of what that looks like. The developer comes up with a list of requests to issue against the service under test, and a response they expect the service under test to respond with. Then they issue those requests against an instance of the microservice that they spun up in a testing environment and compare the actual responses received with the expected responses. Here's another way to represent what this type of testing looks like. The store service is spun up in the testing environment, the developer issues requests against it, and then compares receives response with expected response. This approach is adequate for applications that have simple, predictable internal network traffic. However, the traffic a microservice is handling could be unpredictable, which might be the case if the traffic is generated by user actions, or if it's generated by upstream services that are frequently changing. In addition, the network traffic could be complex. It could have large amounts of data in various formats, which would make it difficult for the developer to create requests that accurately represent production traffic. The second challenge that arises from doing regression tests outside of production is making downstream dependency services available to the service under test. And this is what we mean by a downstream dependency service. If we return to Aaron's e-commerce store, you'll notice the shipping service needs to be available to the store service in order for the store service to handle its traffic. In this case, we refer to the shipping service as a downstream dependency of the store service. And the way to address this challenge depends on whether or not the downstream dependency is internal or external to the application. If the dependency is internal to the application, as is the case with Aaron's e-commerce store, then the dependency could be spun up in the same environment as the service under test. To accomplish this, Aaron would need to coordinate with the team responsible for that shipping service in order to gain access to the most up-to-date version, and then get it up and running in their testing environment. And if the dependency is operated by a third party, which is the case in this example architecture, the approach changes. Because the dependency is owned by a third party, Aaron can't spin it up locally. Instead, they can interact with the actual third-party dependency from their test environment. So when it comes to dependencies that are within the application's architecture, this approach is a good fit when there are only a few simple dependencies downstream of the service under test. When this is the case, it won't take up too much additional effort to spin those up in the testing environment. It's not a good fit for architectures with many complex dependencies because spinning up many microservices in the same testing environment makes that environment brittle. And secondly, it requires those teams to coordinate with one another. One of the main advantages of having a distributed architecture is allowing teams to advance independently, and requiring them to coordinate in order to run tests reduces each team's independence. In the case of third-party dependencies, this solution won't work if the dependency's responses changes over time. So for example, if the dependency returns the exchange rate of US dollars to euros, the data being used by the store service will change every time it is tested, making it impossible to predict what the expected response should be for that set of tests. Now we'll examine a different approach to regression testing called traffic replay and address the same two challenges we just went over. So when it comes to generating the requests and the expected responses to test the microservice with, traffic replay uses recorded production traffic as those requests and responses. So that means instrumentation is added to the production environment, which creates a record of two things: all of the requests sent to the store service and the store service's corresponding response for each of those requests. That record of requests and corresponding responses is then used as the requests to be issued to the service under test and the expected value for each response. So the regression test is similar to before. The updated microservice is spun up in a testing environment and requests are issued against it. The only difference is this time, those requests are from recorded production traffic, not from something developer scripted. And by using recorded production traffic, the developer is spared the effort of predicting what internal network traffic looks like and how exactly the service under test should respond. This makes traffic replay a good fit for regression tests when production traffic is complex and unpredictable. One of the main constraints of using traffic replay is that recording traffic production can introduce complexity into the application's architecture. And if Aaron's store service is handling hundreds of requests per second, creating a record of those request response pairs could require significant addition to the production infrastructure to accommodate the storage of that much data. Traffic replay also addresses the challenge of making downstream dependencies available to the service under test. Similar to traffic replay's approach to the first challenge, the approach here is to record downstream production traffic. That is all outgoing requests from the store service in production and all of the corresponding responses it receives from that downstream dependency. That data is then used to what is called virtualize each dependency. What virtualization means in brief is that for each dependency, a process is started in the testing environment. When that process receives an HTTP request, It searches the recorded downstream production traffic for a similar request that happened in production. And then when it finds that request, it issues the corresponding response that the store received when in production. Now, instead of having to spin up an entire microservice in a testing environment, which can be a long, complicated process, the developer simply spins up a small, lightweight process for each downstream dependency. Virtualizing dependencies is a good fit for testing microservices when that service has many downstream dependencies. In addition, it makes it possible to run tests on microservices that rely on non-deterministic third-party dependencies. With virtualized dependencies, the response for a given request will be the same every time that request is issued. Now we're going to cover what options currently exist for developers who want to use Traffic Replay to test their microservices. Currently, the main enterprise option for Traffic Replay is made by a company called SpeedScale. By charging for their services, they're able to offer a rich feature set, including load testing using recorded traffic and chaos engineering, where the virtualized services are programmed to drop or mishandle requests. However, it's not open source, so it's not customizable. If a company didn't want to pay for their Traffic Replay tool, they could create the one themselves using a combination of already existing open source tools. GoReplay or Stormforge's VHS tool can be used to record and replay upstream requests, and WireMock, Mountebank, or Hoverfly can be used to mock downstream dependencies. And while these open source tools are well supported, making them work together in production and produce easily interpreted results requires a good deal of work from the developer. So if an application is maintained by a small team, they might not need the advanced features of an enterprise Traffic Replay tool, and they might not have the time to develop their own. And this is the use case for Guardrail. It's not as feature-rich as the enterprise options, but it's easier to deploy than the DIY options, making it a good fit for small teams that wouldn't have a very complicated testing scenario and don't have much time to build their own microservice testing tooling. Now that we've discussed what Traffic Replay is and why it's useful to have an open source Traffic Replay tool, James will talk about how we built Guardrail and how it's used.
Thank you, Jordan. So we are capturing traffic in production. Then we have to replay it in staging. That means we have to build for two different environments. So I'm going to show you the overview of Guardrail, its two parts, and then go into detail with a demo. And then I'm going to show how Aaron can detect potential problems early on. So again, this is Aaron's simplified store service. In reality, any service in production may have any number of arbitrary connections. And to make things easier, I'm going to abstract away the gateways in upstream, the shipping service as a downstream dependency. You can imagine the difficulty in adding the recording instruments in an architecture that's already built and running. And by the way, by instrument, I mean a process or tool that captures traffic. So first, we need to insert instrumentation on both sides of the microservice. And then doing that, we have to minimize interruption and changes. We also have to consider the fact that capturing is only temporary. So we need a way to connect and disconnect easily. And then the last concern is inserting an instrument in the path of a request is hard to automate unless we integrate into an orchestration system, if the system has any. So we opted to add the instruments on the host where the service is running to coordinate the recording. Doing it this way, we can take advantage of packet capture from the operating system and then have the ability to use scripting languages to manage the instruments. This brings us to the three different parts of Guardrail. On the production side, it orchestrates the recording instrumentation for capturing traffic. On the testing side, it replays the recording using the same tooling, and the recorded and replayed data are combined to make them digestible. Then they are sent to the reporting service for processing. The reporting service is the one that checks for each responses are different, and it generates a report. It then provides a way for Aaron to see the difference. And that's Guardrail's 3 parts. First, let's look closely at capturing from 2 different sides of the microservice and how the tooling are inserted. I have to mention, though, that for capture to work, it's got to be plain HTTP and not encrypted. Otherwise, we can't capture. On the upstream side, the tool we're using is called GoReplay. It is built for capturing HTTP traffic, and it runs passively without redirecting traffic. It uses a technique called packet capture. And with this technique, IP packets are duplicated on the network interface. It intercepts the traffic on a lower level, though, so GoReplay reassembles the payload to get to the HTTP messages. Once captured, it serializes the intercepted requests and responses into a log file, along with some metadata. It's also capable of doing the reverse. That means it can later read that log file and generate requests for testing. The ability to record and replay, along with the support for a middleware, makes this a good choice for Guardrail. That's capturing traffic on the upstream side. Let's cover virtualizing a downstream dependency with Mountebank. For mocking service dependencies, we opted for Mountebank because it is platform independent, it is well documented, and has a good API. This tool creates virtual services over the network. A virtual service mimics the real downstream dependency by first gathering data in proxy mode. In that mode, it creates a record for every unique request that matches a pattern. We have configured the pattern to uniquely identify a single request so that it can be matched for responses later on. So it stubs request in proxy mode by matching a request to the list of different responses. And then during replay, it responds by using that captured data. So in that mode, you can think of it as a simple server where you send it a request and it gives you the recorded matching response. Sending it the same request again will give you the next recorded matching response. Doing it this way, it can mimic the real dependency. Now, this example shows virtualizing a single dependency, but a service may have multiple. So multiple proxies are needed. The list of dependencies are not known in advance, so a JSON list has to be provided. On init, Guardrail starts a proxy for each of them. Now you ask, how do we insert this proxy? Well, by convention, the URL for the dependency is set on a configuration file. So to use these proxies, Aaron will have to change the configuration of the store service manually. It has to be done manually because the configuration for each microservice is different. Then after loading the changes, the traffic is now going through the proxies. So both tools are coordinated in the same host, and the output is a data directory that contains upstream traffic that can be used for testing and data that can be used to virtualize services. Let's see how Aaron would use it for capturing. First, Aaron declares a list of dependencies in a JSON format. Then he runs the init command. This will start the proxies ready for service mocking. Then Aaron updates the configuration of the source service to use those proxies. And then once updated, he can now start recording. The duration of capture is up to him, and it will depend on his traffic volume. Now, that's capturing traffic in production. Let's look at replaying the captured traffic in a staging environment. To understand what's going on, consider how it would look like to run a single test. We arrange the data for both instruments, then we send one request through and capture the response. Having both the recorded response and replayed response from the same request, we can now make the comparison. To replay all the traffic, the replay service runs all the recorded traffic and captures all of the responses, then sends it to the reporting service, which makes the individual comparisons. The reporting service receives the replay data from the replay service, and it receives those using an API we built using Node and Express. That in turn persists the data in MongoDB for a short duration, and then the node again creates a report from it. Finally, React displays something for Aaron to investigate. Let's walk through how Aaron would run the test and see the results. In a staging environment, Aaron copies over the data directory once, then he starts a store service 2.0 with the same virtual services. Then the replay command runs the rest. The same data can be replayed to multiple versions of the microservice for rapid development and for faster feedback. Of course, traffic replay can be used alongside other tests as well to get more coverage. If any regression is detected, Guardrail shows a simple report. This is how Aaron can catch errors. At the top is a few metrics for performance parity. He can see how the new service compares. He can tell if it's timing out more, if it's returning more error codes, or if it's running longer than average. At the bottom, there's a list of requests that has different responses. They are identified by their correlation ID. Also, it shows the deep comparison of the data in the body in case you'd like to investigate further. And that's how Guardrail helps Aaron run regression tests to a new version before it can cause cascading problems in the entire system. With that, Tim is going to talk about a few challenges that we have encountered.
Thank you, James. So now that we've covered the problem space of testing microservices and why we would want to do that in the first place, and what's so complicated and tedious about that, and we've talked about our implementation of Guardrail and the benefits and improvements that we think it brings to testing microservices. We'll look at some of the challenges that we faced as we implemented our design of Guardrail. Specifically, we'll look at a challenge with mismatched traffic, as well as a challenge at the end when we went to tie everything together. So, mismatched traffic. We noticed that when replaying traffic in a staging environment, responses would sometimes become associated with the wrong request. Hypothetically, this could look something like two pretend users, Alice and Bob, using a microservice, our store service at about the same time. But Bob might get a response that's actually meant for Alice, and Alice will get a response that's actually meant for Bob. And that's obviously not correct, so we need to fix this. Now, bear in mind, this is at least when replaying traffic. So we're in a staging environment. We're not responding incorrectly to real users, thankfully. But the point of Guardrail is testing, and our testing solution can't just mix and match requests and responses however it pleases. They're not interchangeable. So we need to fix this. This is important. So what do we do? So what could be going on here? There's a key phrase in the problem description, and that phrase is "at the same time." This fundamentally is a concurrency problem. So as long as requests are spaced out enough, there is no traffic mismatch. So we just need to limit our service to one user at a time, right? No, that's obviously not acceptable. So what else can we do? let's look a little more deeply at what's causing this problem. So recall how Mountebank, our downstream recording and service virtualization tool, recall how that works when it's replaying traffic, when it's virtualizing services. Specifically, that it pattern matches an incoming request to a stub just being a set of configuration that it uses to generate a response. So the matching stub then generates a virtualized response from a list of one or more recorded responses. So in this diagram, this would be on the right, the R1, R2, R3, etc. If there's more than one recorded response for a given request, Mountebank on each subsequent matching request will iterate through its list of recorded responses, starting over once it reaches the end. And so here, with each request for my address, Mountebank will return R1. And if there's another my address request, it will return R2. And if there's another one, it will return R3, and so on, until it reaches the end, and then it will loop back to R1. So with this behavior in mind, let's re-examine our traffic mismatch problem. A traffic mismatch problem can occur if there are two or more identical requests that are replayed in close sequence about the same time, and Mountebank, our downstream service virtualization tool, has more than one recorded response matching those requests. In such a case, the Mountebank test double, the virtualized service, might return a mismatched response. So we've got to fix this. How can we prevent this from happening? Really what we need is a way to tie together related upstream and downstream traffic so that Guardrail recognizes those as a single contiguous thread. Conveniently, there's already a common pattern in service-oriented architectures that can help with this, and that pattern is called correlation IDs. So what are those? Well, for every incoming user request, for every upstream request, we add an X correlation ID HTTP header. That header's value is a unique request identifier. So this identifier on the initial incoming request is then attached to any related downstream requests and responses, as well as the upstream response back to the user. This way, Aaron and Guardrail can identify every piece of a full request response cycle, including upstream and downstream traffic. So this seems useful, but maybe intricate, kind of detailed, kind of complex. So how do we do this? Well, good news, thankfully, popular web servers like Nginx and Apache both already support this feature, though the naming does vary slightly. Sometimes it's like a request identifier or correlation ID. So this isn't something we actually have to implement ourselves, sort of. We'll put a little asterisk there and come back to that later. So all we have to do is notify Guardrail users like Aaron to ensure that they have correlation IDs or request IDs configured, and also that their microservices won't strip those correlation ID headers out of their requests, but actually continue to pass them along the entire request response cycle, both upstream and downstream, so that any piece of traffic flowing through their microservice, whether left to right or right to left, to ensure that it has a correlation ID header attached to it. So that solves our traffic mismatch problem. With correlation IDs in place, we've solved traffic mismatch. We've enabled Aaron and Guardrail to have a more comprehensive view of their network traffic. So what's next? Well, now we've encountered another challenge. We've got a lot of moving parts here that generate a lot of traffic data, and that data is spread out over several different places, different environments, different directories, different files, so on and so forth. Correlation IDs certainly help, but there's still more work to do in order to distill all of this disparate traffic data into something that is comprehensive and meaningful that Aaron can actually use to better serve his users. So how do we actually tie all these pieces together and then parse and compare the results of our traffic replay tests? As with our architecture, let's kind of take a step back and look generally, consider what exactly we want to accomplish with Guardrail. Ideally, we'd like 3 pieces of data side by side. Number 1 is the recorded user request or upstream request from production. Number 2 is the recorded response to the user from production. And number 3 is the replayed response from staging, from our testing environment. Basically, what our test service responded with when we replayed number 1, when we replayed the user request. For Guardrail's use case, none of this data is very useful in isolation. If we have just the request or just the response or just the replayed response or even 2 out of the 3, it's not that helpful. There's not a lot that we can do with that. We really need all 3 of these pieces combined into a single unit that we can then evaluate. And as James and Jordan and I continue to work through this project, we began referring to this 3-part unit as a triplet. Once again, we have some help. So conveniently, these 3 components of a triplet are actually exactly the information that is included in GoReplay's traffic files, our upstream recording and replaying tool. However, so all the 3 pieces are there in GoReplay's traffic files, but they are spread out all over the place. So Mountebank, our downstream tool, is smart enough to match and group traffic based on correlation IDs, but GoReplay, our upstream tool, is unfortunately not. So for Guardrail to work, we need to do something. We need to turn GoReplay's upstream traffic files into a list of triplets that we can then iterate through and evaluate individually. So on one hand, we thankfully didn't have to implement correlation IDs ourselves. But on the other hand, we still have to do some work with correlation IDs to parse and rearrange GoReplay's traffic files based on correlation IDs. So how do we do that? One naive approach would be maybe to read each of the traffic files into memory and group the entries into triplets, but we wanted something a little more scalable, a little more efficient. And so because all of our data, all of our traffic data, it's HTTP requests and responses, and those are already very commonly represented with JSON. And because our data isn't very strongly related just beyond correlation IDs, correlation ID is the key relation. There's not much relation beyond that. A document store like MongoDB proved to be a perfect fit. Also, thanks to GoReplay's extensibility, I was kind of making fun of it for not being able to do anything with correlation IDs, but on the bright side, it's highly extensible. So we were able to avoid parsing traffic files entirely by writing a GoReplay middleware. And as James covered, our middleware parses components as they arrive, components being HTTP requests and responses. Our middleware parses those as they arrive and forwards them to our reporting service, where the components are assembled into triplets, and then those triplets are evaluated. Basically, the expected response and actual response are compared, and then our reporting service uses that data to generate the test report that James showed. So we've covered a lot of material, and most of it has been quite dense. I want to thank all of you for your patience and your attention. To recap, we examined some of the challenges we encountered in trying to wrangle these 2 sides of traffic into a meaningful, cohesive whole. And we looked at some of the solutions that we implemented to overcome these challenges in what we believe is an efficient and scalable manner. We believe we built Guardrail into an open source tool that is well positioned to deliver significant testing value to engineering teams in charge of budding microservices. The core value delivered by Guardrail is that it abstracts and automates away much of the complexity and tedium involved with implementing and maintaining good, accurate regression tests for microservices. Our hope is that Guardrail can help you prevent your deployed changes from being in that 15% that cause a production incident. Thank you. Any questions? All right, so we've got a couple coming in. Lena asked, great work, Guardrail team. Thank you, Lena. How did we decide on this domain, this problem domain? James and Jordan, feel free to please correct me if I get this wrong, but my memory is that we were looking into like load testing, but there seemed to be a lot of really good kind of simple, easy to use solutions for that. And just as we continued to research load testing, we encountered traffic shadowing, and then I think it was Jordan that actually found the idea of traffic replay, which we don't have to get into the differences there. That would be a whole nother presentation on its own. But that's my memory, is that we kind of started with load testing and wound up here. Got another one from Vahid. Great presentation. Thank you, Vahid. What was the most fun part of working on this project? That's a good question. James or Jordan, do you want to answer that one?
Yeah, I'll take a stab at it. For me, I think it was going from a pretty abstract idea to conversations with people who were working in software engineering, like our mentor Max and Derek and Julius, and them kind of affirming that this is something they could see being useful. And it was fun to go from something that just felt very abstract to something that seemed like it could potentially be used.
Yeah, I'll take a stab. I found it pretty fun to do all the research. Yeah, we did a lot of research, and we read a couple of books just to learn, for example, how service virtualization works, and that was fun for me.
For me, there's so many different things. Probably one of the most fun moments was because there are so many moving pieces to this. The first time like we ran everything together and it worked was just magic. And a lot of that came down to Docker, actually, which I didn't have any experience with prior to Capstone. And James was definitely the driving force behind getting Docker set up and working correctly for us, and being able to just run everything and see it work was awesome. We've got another question in chat. It's on working together as a team. It's from Marcos. Thank you, Marcos. On working together as a team, how long did it take to get in the quote unquote flow of things? And do you have any advice on things you learned working as a team? That's a fantastic question. And that was probably one of the most both challenging and rewarding parts of this is figuring out how to work well together and getting to know each other better. At least for me, I'd say that the getting into flow of things was honestly was a daily was a daily process for me, at least. And it's I think, in my opinion, one of the things that enables a project of this scale is that you have multiple people working together, and everybody sees these things a little bit differently, and is able to give input that somebody else or everybody else in the group might have missed. And I could list off several examples of, we can all three of us could go read the same thing and come back and talk about it. And there were, seemingly very obvious things from what we read that I missed completely, that, James caught, or vice versa. So just a lot of communication every day and learning how to do that, well, how to, have I guess discussions, rather than arguments. Not that, thankfully, I don't think we had many issues with that, but that's a skill, and it's one that when you every time you're in a new group or working with somebody new, you kind of have to tweak and adjust. But it's also very rewarding, a lot of fun.
Yeah, that's great. I'll follow up with Tim. Yeah, we've learned to love the drawing board. So every morning we'd sit around and meet and talk about the entire project on the drawing board, and it's a really good communication tool, and to get everyone looking at the same subject and have the same meaning.
Yeah, I don't have much to add to those two, but yeah, I think visual communication was very helpful, and just sort of trusting each other and relying on each other for sure.
Yeah, we also played to each other's strengths, which was fun.
Okay, looks like there are no more questions. Any final words?
Thank you guys for attending.
Absolutely, we really appreciate it. We hope maybe it piqued some interest or revealed some topics or concepts that might look interesting or appealing. And we really appreciate your time.